Hello, everyone. My name is Leo, and I'm a PhD student from CMU, and today I'm very happy to present my work, Feedback-Guided Adaptive Testing of Distributed System Designs. So to start my talk, I want to give you a quick background about testing and verification, right? When we start computer science, it's actually started by a group of mathematicians. And when they write code, they really want to make sure that the implementation matches the intention. And in 1969, Tony Hoare wrote this nice paper discussing how you can model the behavior of your implementation using logic. And later, when there are more developers writing more general purpose program, the software becomes more complex and verifying the system or the implementation becomes challenging. And in 1990, Barton Miller wrote this paper saying, hey, you don't actually need to, if you cannot verify the entire program, you can actually use testing to find bugs proactively in the implementation. In 1984, when the program becomes more distributed, more concurrent, people noticing that, hey, even designing the algorithm itself becomes challenging when we are trying to implement concurrent and distributed software. And in 1994, Leslie Lamport wrote the paper talking about TLA plus and discussing how people can first design, implement or specify the design of their distributed system in TLA plus to first verify the correctness of their design before implementing them. And now, in 2025, AWS wrote a paper saying, discussing their practice to make sure the correctness of their distributed system. And in the paper, they are saying is that, well, unfortunately, their distributed system become too complex. Even verifying the correctness of their distributed system design becomes becomes a bottleneck. And their solution is actually going back to testing. And what they're saying is that instead of verifying the correctness of their distributed system design, they're actually relying on testing to proactively find bugs in their distributed system. This sounds scary, right? But as a researcher, our job now is to help the developers who design their distributed system to proactively find as many bugs as possible. What does distributed model testing mean here? I have a distributed system, and I can model the behavior of the distributed system and the algorithm using modeling language such as P and TLA+. And the model actually, the state or the behavior of the model is driven by messages shared across different machines. And the testing part is actually to explore the behavior of the distributed system based on different message interleaving. And in this case, the model testing framework will proactively explore different message interleaving to make sure that the behavior of your distributed system model matches the specification. How do we find those schedules? And traditionally, developers rely on random sampling. And let's start with random walk. And the algorithm is actually very easy so that I can just show the entire algorithm in a single slide. You start with a program. And the algorithm will produce a list of schedules. At each step, as long as the program is still running, you take one runnable action randomly. You execute them, you add them to the schedule, and you repeat until the program finishes. And this is how random walk works. Later, developers or researchers have proposed more advanced algorithms, such as PCT and POS. They're trying to constrain the search space, relying on either a formal reasoning, such as partial order reduction, or empirical evidence, such as most concurrency bugs can be observed under a small number of context switches. But there's actually one common issue of all prior work. They're all sampling-based techniques, meaning that it doesn't really scale well for complex distributed systems. Why is that? let's look at two schedules. The only differences across those two schedules is the order between the read messages sent to M2 and M3. From the scheduler perspective, there are different schedules. But if you're familiar with the semantic of the distributed system and their models, they correspond to the same behavior in the distributed system. You are exploring different schedules, but you are actually exploring the same behavior, and this hurts the efficiency. What's missing here? Consider we have a scheduler, and they work really hard in a dark room. They never look outside. They never try to understand what the behavior has explored by the scheduling algorithm, or they neither tries to explore new behaviors proactively. And if you're familiar with software engineering literature, we have seen this problem before. And in the fuzzing world, we start with black box fuzzing. And this is actually what the Buttermiller's paper was talking about. And the algorithm is very simple. You generate some input, and you want to see whether that input will trigger some bug in your program. And people notice that this doesn't scale well for the complex software immediately, such as compiler, because most input you generate will be rejected by the fuzzer. By the parser. It's really hard for you to reach deeper part of your program. And the software engineering community proposed a solution called feedback-gated fuzzing, which is actually very effective. And the idea is also very simple. You pick some input and you perform some mutation. You want to see whether this input triggers some normal behavior in your distributed system or not. You only save those input that triggers normal behavior in your distributed system. In your traditional program. Now the question for us is, can we borrow this idea for the distributed system testing? And I mean, the answer is yes, because the paper is published. And we need to solve two challenges. The first challenge is how do we perform the mutation? In the traditional software, we just perform bit flip for the program input. But we cannot do this for the distributed system because the schedule is actually generated on the fly, not generated beforehand. For example, if there are hard constraints inside the program where the read operation can only happen before the write operation, you cannot generate a new schedule where you want to mutate the order between the read and write operation. For example, in another example, if the elect message can only be produced if all participants send the vote message, it's impossible for you to generate a schedule where the elect message is actually scheduled before the vote message. So the way we solve this problem is through indirect mutation. Assuming we have a schedule, and we perform some random sampling to select a prefix of this schedule. In this case, we use deterministic record and replay to replay the schedule all the way to the prefix. Instead of to continue the record and replay, we actually send here and see what other options we can take. And now, we actually go back to the random sampling. And in this case, we actually generate a new set of schedule which share the same prefix as the input schedule, but have different suffixes. And this is how we achieve indirect mutation. What is even better is that going back to the prior work, we saw lots of prior art trying to impose different heuristics to put the constraints of the search space. And our method is actually adaptive to all prior work. And now we are adding this feedback guidance to all sampling-based techniques. Now we have solved the mutation challenge through indirect mutation with suffix sampling. Let's talk about the second challenge. What makes a schedule interesting? Going back to traditional program, we use code coverage. And in this program, there's actually an atomicity violation bug. But traditional, if we just test this program in a single-threading environment, we can already achieve the 100% line coverage. But we can never trigger the bug. The problem is that code coverage doesn't really capture the semantic of concurrency. And the core of concurrency is the global ordering. How can we identify those orders? And we actually rely on two things. The first thing is formal semantic, where we try to understand whether there are conflict operations, there are lock contentions, etc. And we want to extract those information. And second thing is actually based on our experience talking to developers at AWS. While I was talking to developers, one common request I got from them is they are actually very curious about the behavior of their distributed system and their specific scenarios. For example, if there are requests incoming while the leader election is happening, how can we test this? Well, they can generate a broader scenario through the testing harness, but because of lack of control of the scheduling directly, they can never direct the searching through those scenarios. To solve this problem, we actually designed a combination of diversity feedback and compliance. Sorry. A combination of diversity feedback and compliance feedback. And the diversity feedback tries to extract those interesting happens before relationship through the schedule. And we compare it against a database to see whether we have explored this happen before relationship in the previous executions. If this novel, we increase the diversity feedback and store the schedule. And on the other hand, we actually allow developers to specify the scenario they're interested to test through a domain-specific language. And we want to see whether the schedule is similar to the scenario that is specified developer or not. If so, we increase the compliance feedback. And to combine those two, we identify interesting schedules and to close the fuzzing loop. So to evaluate fast, we actually implement the algorithm inside the P framework, and we collect 94 open and closed source distributed systems, including models from Amazon, DeepSeek, and many prior work. And this is, to date, one of the most comprehensive evaluations to date. And in our evaluation, we noticed that we can achieve up to 41 times higher behavioral coverage, and we can find 33% more bugs in our bug benchmark. And this is the last slide for my talk. In this talk, we talk about FAST, which is a feedback-guided adaptive testing of distributed system designs. And our core idea is to guide the schedule generation through using this feedback guidance. And I'm actually going to define my thesis in 2 weeks. And if you are interested in concurrence testing and you want to see what makes the entire thesis practical, feel free to come to my thesis. And I'm happy to take questions.